Good evening, everyone. In the last class, we discussed about the electric field due to dipole. And in the last class, we discussed about the electric field due to dipole at 2 points. One was at the point on the equatorial axis, and one was the point at axial axis, right? At the axial points, right? We calculated the electric field due to a dipole at axial point as well as at equatorial point. In the last class, we developed the two relations. One was the electric field due to dipole at mm, axial point, and at axial point we found that dipole is nothing. Electric field due to the dipole is 2 kp upon r cube, right? And in the second case we discussed about the electric field due to dipole at equatorial axis, right? And at equatorial axis we found out that electric field due to dipole at equatorial axis is kp upon r cube, right? And there were two major points which we concluded yesterday, the day before yesterday, right? The conclusion one was that the electric field in case of axial point is along the electric field in case of axial point is along the direction of a dipole movement, and in case of equatorial point, right, the electric field vector is opposite to the direction of the dipole movement vector, right? So at equatorial point the electric field vector is opposite to the direction of the dipole movement, and at axial point the electric field vector is in the direction of the electric dipole movement, right? So let's now discuss the electric field due to dipole at some general point, right? We have to discuss the electric field due to dipole at some general point, right? So let's suppose that we have two charges. We can write here electric field due to dipole at general point, right? At general point, right? So at some general point we have to calculate the electric field due to dipole, right? Let's suppose we have the two charges. We know dipole is nothing, it's the two equal and opposite charges separated by a small distance, right? Let's suppose that these two charges are separated by distance, right? This is the center of this dipole. Let me call this as M, right? And let's suppose this distance is given as A and this distance is given as A, right? So the separation between the two charges, minus Q and plus Q, is 2A, right? So the separation D between the two charges will be twice A, right? And at some general point, we have to find the electric field due to this dipole, right? At some general point. Let's suppose this is the point. This is the point. This is the general point where we have to calculate the electric field due to this dipole, right? Let me call this point P, right? And let's suppose this point P is at a general distance of R, right? At some general distance of R. This electric field or this point P is at some general distance of R from the center of this dipole, right? And making an angle of theta with the line joining the two charges, right? It is making an angle of theta with the line joining the two charges minus Q and plus Q. And P is some general point, right? So if we talk about the dipole movement due to this dipole movement, so dipole movement will be nothing. It will be P, right? P will be the dipole movement, P vector, and it will be directed from minus Q to plus Q, right? The dipole movement vector will be directed from minus Q charge to plus Q charge, right? And we know the magnitude of this dipole moment vector is nothing. That's mod of P. That will be equal to charge Q and the distance between these two charges. That's 2A, right? So Q multiplied by 2A will be the dipole moment because of these two charges minus Q and plus Q, right? Now dipole moment is a vector quantity. You know that we can resolve a vector quantity into different components, right? In three-dimensional space, we can resolve a vector in three components, but in 2D space, we can resolve a vector in two components, and both the components should be perpendicular or normal to each other, right? So let's suppose the component of this dipole moment along this will be the cos component. So this will be a P cos theta, right? And the dipole moment along this direction, this will be nothing. It will be P sin theta, right? And we know that any two components of a vector, any two components of vector are independent of each other, right? Two components of a vector which are resolved from a vector, right, are independent of each other and they do not interfere with the other components, right? So p cos theta is the component along p, and p sin theta is a component which is perpendicular to the line joining the p, right? So we can treat these dipoles p cos theta, p sin theta independently, right? So cos theta is one dipole which is directed along p, and p sin theta is another dipole which is directed along, which is directed perpendicular to the line joining the point p, right? So it means that this dipole which is directed along point p, that's the p cos theta component. This dipole will act, or this point p will act as axial point for this p cos theta, right? The dipole, the point P will act as axial point for the P cos theta component, right? And we know that at axial point, the direction of the electric field vector is along the direction of the dipole moment vector, right? So this P cos theta vector is acting as an axial point or the axial dipole moment for the point P. So the electric field due to this will be in this direction. Let me call this as this electric field as AB, right? So this electric field will be along this direction, along the dipole moment vector, right? So this will be the direction of this electric field vector due to this P cos theta component. Let me call this electric field vector as AP, right? And talking about the P sin theta, we know that point point P for this P sin theta component acts as equatorial point, right? Point P for this P sin theta component, the component of the electric dipole moment, which is perpendicular to the line joining the point P, acts as the axial point, right? So point P is axial point for P sin theta, right? It means that point P is, axial point for P cos theta, right? And P is equatorial point for P sin theta, right? So it means that we know that for the at the equatorial point for a dipole moment, the electric field is directed opposite to the direction of the dipole moment, right? P sin theta is directed in this direction. So at this point, the electric field due to P sin theta component will be opposite to that of P sin theta component, right? So this will be the component, right? So this will be the component, right? Let me call this as EA, right? And the resultant of EA vector and EB vector will give us the resultant electric field at general point P, right? Let's call that resultant electric field as E. So this will be the resultant electric field, right? This will be the resultant electric field. Let's call this resultant electric field as E, right? So E vector will be nothing. That will be equal to EA vector, right? Plus EB vector. So angle between EA vector and AB vector is equal to 90 degree, right? You can see clearly that EA vector and EB vector are inclined at an angle of 90 degree with each. So let's suppose that angle alpha is made by the resultant of the electric field vector with the EB vector, right? Angle alpha is made by the resultant of this electric field vector with the AB vector, right? So this will give us the direction of the resultant electric field vector, right? And we know that EB is the electric field at the axial point for P cos theta. So EB has to be equal to twice Kp. P is P cos theta, so it will be twice Kp cos theta, right, upon R cube, right? And similarly, our EA will be equal to EA for dipole moment P sine theta. Point P is equatorial point, and we know that the magnitude of electric field at equatorial point is nothing, it's Kp by r cube, and P here is P sine theta, right? So Kp sine theta over r cube, right? So this will be the electric field because of electric field at point P because of P sine theta, and electric field at point P because of P cos theta component, right? And these two vectors are perpendicular to each other. It means that the resultant electric field vector, or the resultant of the magnitude of EA and EB, will be EA square plus EB square, right? So it will be nothing. It will be 2 kb cos of theta upon r cube for whole square plus kp sin theta upon r cube whole square, right? So from here we can just take kp by r cube outside, right? Kp by r cube. So it will be under root of, will be left here with 4, it will be 4 times cos square theta, right? Plus sin square theta, right? So we can rewrite it as this, our magnitude of the resultant electric field at some general point P, Kp upon r cube. So we can rewrite it as 3 cos square theta plus cos square theta plus sin square theta, right? We know that cos square theta plus sin square theta is equal to 1. We can substitute the value of 1 in place of sin square theta plus cos square theta. So the magnitude of the resultant electric field at point P will be Kp upon r cube under root of 3 cos square theta plus 1. So this will be the resultant of the net electric field vector at point P at some general point P, which is at a distance of r from the middle of this, from the midpoint of this electric dipole, right? So this will be the final equation, right? At some general point. So this is an equation for a general point, right? We can just cross check this equation as well. Let's suppose for axial point, for axial point, theta will be equal to 0 degree, right? Theta will be equal to 0 degree for axial point, right? It means that we can put theta equal to 0 degree in this equation. So A will be nothing. That's Kp upon r cube. So cos 0 is 1. So that will be 3 cos 0 plus 1. But that will be equal to cos 0 is 1, 3 to 1 is 1, plus 1 is 4. So it will be twice Kp upon r cube, right? So this is the same result we derived earlier, right? When the point P was at some axial point, right? Because of the dipole moment, because of the dipole, the electric field at axial point is 2 Kp upon r cube, right? And similarly, for equatorial point, theta will be equal to 90 degree, right? Theta will be equal to 90 degree. And we know that cos 90 degree is nothing, that's equal to 0, right? You can put the value of cos 90 in this equation, right? And we will get the value Kp upon r cube under root of 3 cos 90, 3 cos square 90 degree plus 1. So that will be equal to 0, or electric field at equatorial point will be once again Kp upon r cube, right? Kp upon r cube will be the electric field at equatorial point. So it means that the equation that we derived is correct, right? It's a correct equation. So this is the general equation for the calculation of the electric field at some general point in case of dipole, right? So Kp upon r cube 3 cos square theta plus 1, where r is the distance from the center of the dipole and theta is the angle which the point which the line joining the point makes with the dipole moment, right? With the dipole moment, right? So that's it for this. And if we calculate the direction of this resultant electric field vector, we have to calculate this alpha, right? Alpha. So we know that EA and EB are perpendicular to each other. So tan of alpha will be nothing. We can calculate the tan of alpha. So tan of alpha will be nothing. It will be EB upon EA, right? EB upon EA. So tan of alpha will be, sorry, it will be EA upon EB, right? EA upon EB. EA upon EB. That will be the tan of alpha, right? And EA is nothing. That's equal to, EA was equal to Kp sin theta upon R cube, right? That's Kp sin theta over R cube upon EB. That's twice Kp cos theta over R cube, right? This R cube will get cancelled, 2 Kp and 2 Kp will get cancelled, not 2 Kp, only Kp will get cancelled, will be left with sin theta over 2 cos theta, right? So sin theta over cos theta is nothing, tan theta, so you can write it as half of tan theta. So from here, alpha is nothing, it's tan inverse of half of tan of theta, right? So this will give us the direction of the resultant electric field vector at some general point due to this dipole, right? So this completes our the electric fields, right? We discussed about the electric field due to point charge. We discussed about the electric field due to sphere, due to infinite sheet, due to infinite line charge density, right? And then we discussed the electric field due to dipole as well, right? And the Gauss law and the flux has already been discussed. Now we'll be discussing some of the problems related to electric field due to dipole, and also some of the questions which was asked previous years in previous years. We'll be discussing that today. And in the next lecture, in the next class, we'll be starting with the potentials, right? Potentials and capacitors, right? So let's begin with the basic question here. The question is that it's a very basic question. The question is the distance between the two charges plus q and minus q of a dipole is r, right? On the axial line at a distance d from the center of dipole, electric field intensity is proportional to, right? So we know that we calculated for dipole on an axial line, right? On an axial line. So this is our axial line, right? This is some point P, and let's suppose from the center of this dipole, the distance is d, right? And we calculated that this electric field vector is nothing, it is inversely proportional to d cube, right? Here, in the last lecture, we used the symbol r, so it means that the electric field vector was inversely proportional to r cube. So here, if we take d as a symbol, so it will be inversely proportional to d cube. So this will be the this will be the correct option, that it will be inversely proportional to the d cube, right? It means our electric field vector will be inversely proportional to the d cube, right? So this is our question number 2. Let's discuss question number 2 here. The question 2 says that two electric dipoles of dipole moment P and 64P, right? We have two electric dipoles, one of dipole moment P and another of dipole moment 64P, right? Are placed in opposite direction on a line at a distance of 25 centimeter. The electric field will be zero at some point between the dipoles whose distance from the dipole of moment P is, right? So it means that we have two dipoles, right? Let me represent the dipole with this. So this is the negative end of this dipole, right? This will be the positive end of this dipole, right? And another dipole is here. This will be negative. They are directed are opposite in direction, right? they're opposite in the direction. So this is the dipole, right? It's another dipole. So it will be directed along this, right? So they are separated by a distance of, the separation between these dipoles is given as 25 centimeter, right? So 25 centimeters the separation between the two dipoles, right? And we know that the electric field due to dipole on its axial line is along the direction of dipole moment, right? For this dipole electric field at this point, let's suppose at a distance of let's suppose that this is our dipole moment P, right? And this is our dipole moment of 64P, right? And let's suppose we're placing this dipole at a distance of x from here, and the distance from this dipole will be then 25 minus x, right? And because of this dipole P, because of the dipole of dipole moment P, the electric field vector will be directed along the dipole, right? And it will be directed like this. Let me call this as EP, right? EP. So this is the electric field route of the dipole P. That's EP. And because of this dipole, electric field will be once again along the dipole moment of the 64P. So it will be in this direction. Let me call this as EQ, right? EQ. I'm calling this as EQ, right? So the net electric field has to be zero, right? Net electric field has to be zero. It means that net electric field will be only zero if the two electric fields cancel out each other, or the magnitude of the EQ is equal to EP, right? So therefore, EP has to be equal to EQ, so that the net electric field at some point between the two dipoles is equal to zero, right? So EQ will be nothing, its actual point, so it will be K twice K. Dipole moment is 64P upon x cube, right? It will be x cube, and EP will be nothing. So EP will be equal to twice K into P upon 25 minus x ka whole cube, right? 25 minus x ka whole cube, right? But let's equate them. So 2q into 64p, right, upon x cube, that will be twice kp upon 25 minus x ka whole cube, right? So this 2kp and 2kp will go, right? So we'll be left with 64 upon x cube, that's 1 upon 25 minus x ka whole cube, right? So we can rewrite it as like this. 64 will be equal to x upon 25 minus x ka whole cube, right? If we calculate the cube root of 64, that will be equal to x upon 25 minus x. And the cube root of 64 is nothing, that's equal to 4, right? We know that 4 cube is 64, right? Or cube root of 64 will be 4, right? So it will be 4 here, x upon 25 minus x. Or we can write it as 1 upon 4, it will be equal to 25 upon x minus 1. So it will be 5 upon 4 will be equal to 25 upon x. So this will be cancelled out with 5. Or x will be equal to, that will be 20, right? 20 centimeter. So x comes out to be 20 centimeter. So x is the distance from 64p, right? If this is 20 centimeter, then this distance has to be 5 centimeter, right? So it will be at a distance of 5 centimeter from dipole moment P. So E will be 0. E will be 0 only at a distance of 5 centimeter from dipole moment P. From dipole of dipole moment P. So at a distance of 5 centimeter from P, the electric field due to dipole will be equal to 0, right? This is another basic question here. If the magnitude of intensity of electric field at distance x on axial line and at a distance y on equatorial line on a given dipole are equal, right? So it means that electric field at axial line is equal to electric field at equatorial line, right? Magnitude. We're talking about the magnitude only, right? Correct. So at axial line, we know that the electric field will be 2 kp upon x cube, right? And at equatorial point, the electric field will be 2 kp upon y cube, right? We have to find the ratio between x and y. So this will go right. Equatorial on a given line are equal, then x ratio y, right? So I have to find the x ratio y. So it will be 2 here. So x upon y ka whole cube, right? Or we can write it as it's cube root of 2, that's x ratio y, right? So x ratio y is nothing, it's the cube root of 2, right? So for ratio cube root of 2, the electric field at axial line and the equatorial line is equal, right? And this is the another question here. The question is from with respect to the electrostatic lines of force. The question is a very simple and basic here. Which one of the following patterns of electrostatic lines of force is not possible, right? We know that there are certain properties, right, that electric field lines carry with itself, right? And one of the important property of electric field lines is that it does not follow it does not form closed loop, right? Electric field lines, electric field lines due to static charges, right? Due to static charges, it does not form closed loop, right? Electric field lines do not form closed loops. But when there is an electric field due to induced magnetic field, right? When magnetic field induces electric field at some region, right? In some space or region, then that electric field is not a conservative in nature. That's a non-conservative electric field. That electric field forms the closed loop, right? That electric field do form the closed loop, but the electric field due to static charge or the electric field due to the electric field lines due to the conservative fields, right? Due to the conservative electric field that do not form the closed loop, right? But when the electric field is induced because of the magnetic field, right, that we will study in the electromagnetic induction, where electric field is actually induced because of the magnetic field, right? So, but the electric field induced there do not form the closed loops. That's not a conservative field. That's a non-conservative field, right? So that form a closed loop. Here it does not form a closed loop, right? So electric field has the basic property that they do not form the closed loop. We can see in option number 1, the loops are not closed, right? This is a uniform electric field. So this is a possible electric field, right? This represents a uniform electric field, right? And option number 2, it represents the electric field due to line charge, right? Due to line charge, correct? Sorry, due to point charge, not line charge. So this is the electric field due to point charge field, right? And the option number 1 represents the uniform electric field lines. And we know that for infinite non-conducting sheet, the electric field lines are uniform or constant. So it represents the electric field lines due to infinite non-conducting sheet, right? So option number 2 forms the electric field lines due to point charge and it does not form the closed loop. So this is a possible electric field, right? And option number 4 is also a possible electric field, right? But option number 3, here you can see that the electric field lines form the closed loop, right? They form the closed loop. And we know that electric field lines due to static charge do not form the closed loop. So this option is not a possible option, right? This option is not a possible option. So we can say that this option is not possible, right? So option number 3 is not possible, correct? Because it forms a closed loop. Another good question here. This question was asked in NEET few years back, right? Electric charge is uniformly distributed over a long straight wire of radius 1 mm, right? The charge per centimeter length of the wire is q coulombs, right? So the charge per centimeter of this wire is q coulombs, right? A cylindrical surface of radius 50 centimeter and length 1 meter encloses the wire symmetrically, right? As shown in the figure. So this is our cylinder. This is the cylinder, right? This is the cylinder. And this is our line charge, right? It's placed symmetrically here inside this cylinder, right? We have to calculate the total flux passing through the cylinder surfaces is, right? So this cylinder encloses a line charge, right? It means the cylinder encloses some charge because of this line, right? If the charge, some charge is enclosed by the cylinder, then because of that charge, there will be electric flux associated with the cylinder, right? And we know that total electric flux through the closed loop, through the closed surfaces is nothing. It's the charge enclosed upon the epsilon naught, right? And we know that charge enclosed by this cylinder is from this point to this point, right? This is the total charge. And the length of this line from bottom of this cylinder to the top of the cylinder is equal to 1 meter. And it has been given that the charge per centimeter is q coulombs. So it has been given that the charge per centimeter is q coulombs. It means that for 1 centimeter, the charge is q coulombs. And for 1 meter, that's 100 centimeters, the charge q will be equal to 100 coulombs, right? 100 q, right? It will be 100 q, right? So the total charge enclosed is 100 q. So the flux associated with this cylinder will be nothing. It will be 100 times q upon the epsilon naught, right? 100 times q upon the epsilon naught. So the only correct option for this is option number 2. So 100 q upon epsilon naught is the perfect answer, right? So another question here. The question is, a hollow cylinder has a charge q coulombs located within it symmetrically, right? There's some charge here placed symmetrically. Charge is q, right? It is placed symmetrically within this cylinder, right? If phi is the electric flux in units of voltmeter, right? Associated with the curved surface, right? With the curved surface, it is given that the phi is the associated flux, right? The flux linked with the plane surface A, and the plane surface B, right? Correct? And we know that this is a closed surface. And inside the closed surface, the charge Q has been placed. Whether the symmetrically it's placed or it's not placed symmetrically, right? Uh, the total flux will be nothing. It will be equal to charge enclosed upon the epsilon naught, right? And this total flux will be the flux through the curved surface and flux through the area A and the area C, right? So this flux will be linked with the three surface. One will be the covered surface area of the cylinder. Another will be the flux through the plane surface A. Another, then third one will be the flux linked with the plane surface C, right? So we can write here this phi as phi through curved surface, right? Plus phi through this plane A and phi through this plane B, right? That will be equal to charge enclosed upon the epsilon naught, right? And we know that the electric field, this point charge will be like this, right? So this will be the electric flux due to this point charge. It means that whatever the flux through curved surface, whatever the flux through plane surface C, which same will be the flux associated with the plane surface A, right? So it means that the flux through A, phi A will be equal to phi B, right? Phi A will be equal to phi B. So we can write it here. Phi curved surface will be equal to plus phi A plus phi B. We can write it as twice phi A. That's charge enclosed Q upon epsilon naught, right? Correct. We have to calculate the phi A. And this phi through curved surface is given as uh, phi, right? This is the phi that's given as electric flux through the curved surface area. So we can write this phi curved surface with phi, can replace it with phi, so it will be twice phi A. That will be equal to Q upon epsilon naught, right? We have to calculate this phi A. So twice phi A will be equal to Q upon epsilon naught minus phi, or phi A will be equal to 1 upon 2 Q upon epsilon naught minus phi, right? So this will be the linked electric flux through the plane surface, right? So from this, option number 2 is the correct answer. That's 1 upon 2 q upon epsilon naught minus phi. This will be the flux through plane surface C and the plane surface A, right? This will be the flux. So that's it with respect to the electric fields, right? Electric field lines or the electric field due to dipole. We completed almost everything about the electric fields, right? We discussed about the electric field due to point charge, due to line charge, right? Due to all other charge distribution. And then we discussed about the Gauss law and flux as well. And then finally we discussed about the electric field due to dipole, right? Let's suppose that if there's a question like this, suppose that this is a sphere, right? Or any closed surface, right? Sphere or any closed surface. Let me take sphere, right? Let me take a sphere, right? Let's suppose that I'm placing a dipole, right? Dipole. So I can frame a question that an electric dipole, an electric dipole, an electric dipole is placed inside a sphere, right? Inside a sphere. If an electric dipole is placed inside a sphere, then total flux, then total flux through the sphere will be. And we know that total flux is nothing. That's equal to whatever the charge enclosed upon the epsilon naught. And with respect to the dipole, the total charge of a dipole is zero, right? These are two equal and opposite charges. So for any dipole, the total charge is equal to zero, right? So the Q enclosed for this sphere will be equal to zero, or we can say the flux because of this dipole will be zero through this sphere, right? But the electric field will not be zero, right? Electric field will be there. Let's suppose this is the point P here. And because of this minus Q charge, the electric field will be in this direction. Because of this plus Q charge, the electric field will be in this direction, right? This will be the electric field, right? And there will be some net electric field like here, right? So the electric field will be there, but the total flux through this sphere to dipole will be equal to zero, right? So that's it for today. We'll meet in the next lecture and we'll be discussing about the electric potential and capacitors. Till then, take care and goodbye.